Hi, I'm Mr. Green here. I'm going to be taking you through the fifth lesson of the physics topic, atomic structure and radiation. This lesson focuses on half-life, and our objective is to learn what half-life is. If you could pause the video and write that down as your lesson objective. Okay, so our retrieval questions. We've got 5 questions as always for retrieval. If you could pause your video and please attempt those. Okay, question 1. Which type of radiation is the most penetrating? The most penetrating type of radiation is gamma radiation. It can travel an unlimited distance in the air, whereas the others get stopped by alpha by paper and beta by aluminium. Question 2. What type of radiation is the most ionizing? So the most ionizing, the most effective would be alpha. It's got the largest mass, it's got the largest charge, it's going to encounter a lot more particles because of its size. Gamma is the least ionizing because it's got no mass. It's going to pass through a lot of materials, as the atom is mainly empty space. It's going to pass through a lot of those without having any effect at all. Question 3. What can stop beta radiation? Beta radiation can be stopped by a sheet of aluminium, quite a thin sheet of aluminium, 5 mm thick. Question 4. What makes up an alpha particle? 2 protons and 2 neutrons make up an alpha particle. And finally, question 5. What's the unit of radioactivity? Referred to that in the first lesson. It is the becquerel, named after Henri Becquerel. Okay, our learning outcomes today is to calculate the half-lives of radioactive isotopes, look at examples on the board and try and explain them. Okay, so start off with our starter. So we need to imagine a company. A company's got 1 million phones and sells half of its stock every day. How long does it take them to sell all of their stock? Okay, if you pause the video, try and work that out. Bit of a puzzle for you. Give yourselves a minute. Okay, so the way we need to attack this one is we need to keep halving and halving until we reach the number that's basically 0. You should be able to work out, if we just keep halving a number, it's never going to reach 0 eventually. It won't get to 0 at all, but we can get fairly close to that. We can get to a number that's basically so small it's insignificant. So we start off with 1 million phones. If we keep halving that, 1,000,000, 500,000, 250, 125, 62,500, 31,250 and 15,625, how many days is that? 1, 2, 3, 4, 5, 6. So in 6 days, it's gone down to that point. Next one. How many days to get down to 244.1 if it halves every single day? 1, 2, 3, 4, 5, 6. So in 12 days, it's gone down to 244, not quite 0. Try again to get down to 3.75. How many days if it halves every day? 1, 2, 3, 4, 5, 6. So that's 18 days. 18 days to get down to 3.75. Continue halving that until we get to 0.9, a number which we would say is as close to 0 as we're really going to get. 2 days on there. So in total, how many days to go from 1 million to around 0? We need to count the number of arrows that we've got there, which gives us 20 days. So 20 days for a company to sell 1 million phones if it sells half of its stock every single day. Moving on then, radioactive decay. What is the definition of radioactive decay? Well, we define radioactive decay as the process by which an unstable atom would release radiation from the nucleus. So what's these pictures at the bottom about? The pictures at the bottom are an indication that radioactive decay is random. We do not know which nucleus is going to decay next. We cannot tell which one's going to decay, so we can't predict that. But if we have a large enough number of nuclei, we can predict how many will decay in a certain amount of time. We just don't know which ones will. We know how many of them will. We couldn't be able to say individually this atom, this atom, this atom. But if we had a large number of nuclei, we'd be able to state this number are going to decay in a certain amount of time. This refers us to the half-life. 2 definitions for half-life. Please get both of these down and commit them to memory. Half-life is the time it takes for the number of radioactive nuclei of the isotope in a sample to halve. Or the time it takes for the count rate from a sample containing the isotope to fall to half of its initial level. Get those down, try and memorize them. Okay, so to try and demonstrate that, how do we read half-life from our graphs? Okay, so what's the half-life of the substance shown in the graph? Well, first off, we need its initial count, the initial number of radioactive nuclei. We can see from the graph that that's 60. So what would half of that be? Half of 60 would be 30. So on our graph from 30 we read across until we hit the line of the graph, and then we read down. How many days for it to fall to 30? 4 days. Now we can confirm that by going half again. What's half of 30? 15. 15 across until it hits that graph will come down at 8 days. 8 take away 4 would be 4 days. We've confirmed the half-life of that sample is 4 days. It took 4 days for it to fall from 60 to 30, and then 4 days more than that to go from 30 to 15. Half-life of that was 4 days. Try it yourself. Pause the video, calculate the half-life of the following decay curves, and don't forget to put your units on there as well. Okay, pause the video and attempt those. Okay, so for our first graph there, we'll see the initial count rate is 80. So we want the time taken to fall to 40. Draw a line across on our graph, comes down, takes around 2 days. To confirm, we do it again. 20 across, down to 4, gives us 2 days. In an exam, if you're asked to do this, if you're asked to calculate the half-life from a graph, you need to draw those lines on your graph. You get an extra mark for every time, not every time you draw it on there, but if they can see you have used those lines drawn on the graph, you get marks for doing that. Our second one, the strontium-90, we can see its initial got 100 grams of it, and the time at the bottom is in years, so be careful. So how long to fall to half its count? Well, to go from 100 to 50, it took 25 years. And to go from 50 to 25, it took another 25 years. So its half-life is 25 years. Again, that second one is just for confirmation we got the first one right. Okay, so let's say we have a strawberry cable. We're going to plot the height of the cable at the start of our graph, and every 30 seconds we bite half of the strawberry cable. Then plot the new height on the graph. We're going to repeat this process until the strawberry cable is too small to halve. If we did that, our graph would look like this. So we'd start with 40 centimetre cable. After 30 seconds, we'd bite it so it was 20. Another 30 seconds, so it was 10. Another 30, so it was 5. Another 30, 2.5. Then eventually it gets to the point we can't halve it anymore. That would be our graph. That would be our curve. And our half-life in that case, looking on the graph, would be 30 seconds. So the half-life of a radioactive isotope is the average time it takes for the number of nuclei in the isotope in a sample to halve. The activity is the number of nuclei that decay per second. The number of radioactive isotopes and the activity decrease by half every single half-life. We can calculate a half-life without a graph. So, question, if 1/8 of an original radioisotope is left after 6 days, what's the half-life for the sample? Pause your video whilst you attempt this. Okay, so 1/8 is 3 half-lives. Okay, so 3 half-lives have passed in those 6 days. If 6 days is 3 half-lives, how much is 1 half-life? That would be 2 days. Radioisotope has a radioactivity of 10,000 counts per second. What's the activity of the radioisotope after 3 half-lives? Pause the video and try and attempt that. Try and use the method I used for the mobile phones at the start. Okay, so first one 5,000, second one 2,500, third one 1,250 counts per second. So we half it, we half it, and we half it again. Gives us a count rate of 1,250 counts per second. Okay, quick progress check. Please pause the video while you attempt these 3 questions. Okay, question 1. Define the half-life of a radioisotope. It's the time it takes for the number of radioactive nuclei of the isotope in a sample to halve, or the time it takes for the count rate from a sample containing the isotope to fall to half its initial level. Question 2. A radioactive isotope has got a count rate of 500 counts per second. What's its count rate after 4 half-lives? So we'd have to do 500 divided by 2, that answer divided by 2, that answer divided by 2, and that final answer divided by 2. Gives us 31.25 counts per second. Question 3. A radioactive isotope has a half-life of 15 hours. A sealed tube contains 8 milligrams of this isotope. What's the mass of the isotope after 15 hours? And what's the mass after 45 hours? Okay, so 15 hours, 1 half-life has passed. So if its initial mass was 8, half of 8 would be 4. For B, the mass is 45 hours later. That would be how many half-lives? 3 half-lives. So 45 would be 3 half-lives. We get 8, divide that by 2 to give us 4. Another half-life, divide that by 2 to give us 2. And another half-life, 2 divided by 2 gives us 1 milligram. Okay, to finish off, a couple of exam questions. Please pause the video while you look at these. Technetium has a short half-life and emits gamma radiation. What's meant by the term half-life? And a sample of rainwater contaminated with iodine 131 gives a count rate of 1,200 counts per second. Calculate how many days it would take for the count rate from the sample of rainwater to fall to 75 counts per second. Half-life of iodine 131 is 8 days, and show how you work out your answer. Pause the video while you do that. Okay, answers for this one. Question D. Technetium has got a short half-life and emits gamma radiation. Half-life is the time taken for the number of radioactive nuclei in an isotope sample to halve. Question 2. How many days will it take for it to fall? So we've got starting our count rate of 1,200. How long to get to 75? So 1 half-life 600, 2 half-lives 300, 3 half-lives 150, and 4 half-lives 75. So it takes 4 half-lives. If 1 half-life is 8 days, we do 4 times 8 to give us 32 days to fall to that level. Finally, a question concerning half-life. Again, in the exam you would need to draw your lines on this, but pause the video whilst you attempt that question. Okay, so technetium-99 is used by doctors as a medical tracer. In hospitals, it's produced inside a technetium generator by the decay of molybdenum-99 nuclei. Lots of big words there, just need to know that they are atoms. The figure below shows how the number of nuclei in a sample of molybdenum-99 changes with time as the nuclei decay. A technetium generator will continue to produce sufficient technetium-99 until 80% of the original molybdenum nuclei have decayed. After how many days will the source of molybdenum-99 inside a technetium generator need replacing? Show clearly your calculation and how you use the graph to obtain your answer. So what we want to know is how long is it going to take for that count rate or that number of nuclei to form to 80% of 100,000. 80% of 100,000 would be 20,000. So we draw a line across at 20,000 and it comes down at 6 days. 6 days would be the time taken, or the days that we would need to replace it, because we need it to be above 80%. Okay, thanks again for your time there. Please review the screencast again if you need to know anything else, and I hope you found it useful. See you again soon. Goodbye.